In this lesson, we're going to continue to look at ways in which we can prevent iron from being oxidized, and in this particular case we're going to take the example of an oil platform in C, and being made from iron, it is clearly vulnerable to oxidation and rusting. So if there's no protection there at all, then the iron is going to rust. Okay, there we go, it's turned to rust. What happens when it rusts? Well, as we saw in the previous lesson, iron reacts with oxygen that's present in the water, in this case the seawater. It'll form iron oxide, which becomes hydrated, and that forms rust. So rust is really hydrated iron 3 oxide. Just repeating that again. And during this rusting process, what's happening is the iron is being oxidized. Let's say it's having its oxidation state increased to +3, and it loses electrons. If we're going to stop this oxidation process happening, we've got to find a way of preventing the iron from being oxidized and losing its electrons. So we want to prevent this reaction taking place. Now, in the previous lesson we learned that one of the ways we could do that is using something called sacrificial protection, but in large scale structures like this oil platform, for example, another more practical method is often adopted, which is that of cathodic protection. And in cathodic protection, rather than using a sacrificial metal to stop the iron from losing its electrons, we use a power supply which is connected to an inert anode like this. So the anode is positive, the cathode is negative, and the electrons in this circuit are pushed by a power supply, by a battery, in this direction from the anode onto the cathode. And because these electrons are being pushed onto the oil rig by the power supply, the iron in the oil rig is unable to lose electrons because it's receiving electrons from the power supply. So we can say that the iron cannot be oxidized because it cannot lose electrons, as this half reaction so demands, because it's receiving electrons from the power supply. Okay, so effectively what we've got here is electrolysis. We've got an anode, we've got a cathode that are immersed in an electrolyte, and the electrolyte contains effectively 4 ions. Okay, we've got sodium plus ions, we've got chlorine minus ions, we've got hydroxide ions, and we've got hydrogen ions. Since the cathode is negative, the hydrogen ions are going to migrate towards the oil rig. When they come in contact with the oil rig, it's going to be the hydrogen that receives the electrons. The hydrogen is going to be reduced because it's much lower down in the reactivity series than sodium. So we're going to get hydrogen being reduced here. So we can write the half reaction for the cathode, H plus E minus, gives us a hydrogen atom, which will double up with another hydrogen atom to find a hydrogen molecule. We balance the equation. Okay, and that's the half equation for the cathode. So you're going to get hydrogen building up and being released from the oil rig. And in the case of the anode, well, both chlorine and the hydroxide ions will migrate towards the anode, and both of these will tend to be oxidized. So you're going to get oxygen and chlorine gas being released at the anode. So we can write the half equations for the anode. Just bear that down, I just had to make a bit of space. Alright, so we can write Cl minus. The chloride ions will lose an electron to form chlorine gas, while the hydroxide ions will also lose an electron to form water plus oxygen plus 4 electrons, and we put a 4 there to balance the equation. Okay, so those are the electrode half reactions for the anode. Alright, so you're going to get bubbles of oxygen and chlorine gas being given off at the anode, which I should have mentioned earlier is typically made from titanium. Okay, and titanium, although it is quite high up in the reactivity series, it is, like aluminium, very unreactive indeed, because it has a protective oxide layer which effectively renders it inert